So welcome to the OU Speakers Series. Really appreciate you turning out on a Thursday night before spring break. We particularly want to thank the Sam Noble Museum for providing this wonderful venue for the Speakers Series, and we also thank the museum for hosting a Galileo's World exhibition on Galileo and microscopy that's upstairs in the Higginbotham Gallery. This semester, the Sam Noble exhibit is devoted to the story of early microscopy. It features a work by Galileo's friends that's the first published report of observations with a microscope. It's an unusual document. It's one-fourth of all the copies in the world are upstairs on display. It's one of 4 intact printed copies that have survived. Now, for information about this or other exhibits in the Galileo's World exhibition, check out the exhibit website at galileo.ou.edu. Now, tonight is one occasion of the OU Speakers Series here this semester that features faculty from the OU campus with expertise relevant to Galileo's World. This series occurs on the second Thursdays of each month throughout the semester. Each presentation, including tonight's, is followed afterward by a skywatch out on the museum lawn hosted by astronomy professor Mook Killick and the student group, the Lunar Sooners. So be sure to stop by and say hi to them and see what they have planned for us tonight. It's a great way of participating in Galileo's World. We also thank the Department for the History of Science, Technology, and Medicine for their many contributions to Galileo's World. And most of you are familiar with the department, but in case not, the University of Oklahoma is one of the few institutions where a student may earn a master's or a doctoral degree actually in the history of science. In addition, every semester, the History of Science department offers distinctive opportunities for students in any major. This spring semester, the department is teaching 16 undergraduate courses with a combined enrollment of 535 students. Some of these undergraduate students may choose to go on with future courses and earn a minor or a second major in the history of science. 4 History of Science department graduate students served as co-curators of the Galileo's World exhibition. Brent Perkable, James Burns, Carolyn Skirse, and Jackson Pope. And Dr. Jared Buss, a recent graduate of the department, is the sole curator of the Quest for Other Worlds exhibit located on the main floor of Bazell Memorial Library. His presentation last month in this OU Speaker Series is now on the galileo.ou.edu website, where it will soon be joined by tonight's presentation. The 12 faculty in the History of Science department span a wide range of subject areas, chronological periods, and geographical regions. 2 weeks ago, we assembled an outstanding panel of distinguished international speakers for the Galileo's World Symposium on February 25th. Yet suppose another university were to assemble a panel of distinguished scholars, all with expertise relevant to Galileo's World in the history of science. They could not do better than to draw all of their speakers from OU's Department of the History of Science. So this semester in the OU Speaker Series, we are privileged to hear from several of these faculty. Next month, Professor Renk Vermeij will address the telescope in the scientific revolution, looking at the world with new eyes. And tonight we have a special dual presentation on astronomy in the Renaissance by Professors Kathleen Crowther and Peter Barker. Professor Crowther earned her PhD in the history of science from Johns Hopkins University in 2001 and joined the OU History of Science department in 2002. Her many publications include the work Adam and Eve in the Protestant Reformation, published by Cambridge University Press in 2010. Professor Barker earned his PhD in philosophy from the State University of New York at Buffalo in 1975 and joined the OU History of Science department in 1995. His many publications include substantial contributions to areas as diverse as early modern astronomy, science in the Cold War, and the philosophy of science. As just one example, his book, The Cognitive Structure of Scientific Revolutions, published in 2006 with co-authors Hannah Anderson and Zhang Chen, combines scholarship in the history of science with a critical philosophical assessment of the nature of scientific change. The contributions of Professor Crowther and Professor Barker to Galileo's world have been immense. Each proposed and taught a dream course related to Galileo's world. Last semester, Professor Crowther designed and taught a dream course on the scientific revolution. This semester, Professor Barker designed and is teaching a course on science and civilization in Islam. Professor Barker has also made available for free download his translation of Galileo's Starry Messenger. In addition, they have co-written an article on images in late medieval and early modern astronomical texts that is forthcoming in ISIS, the leading international journal in the history of science. Perhaps some of tonight's presentation may pertain to that article. Or perhaps I'll be corrected, or that will be clarified in a moment. In any case, please join me in welcoming Peter Barker and Kathleen Crowther for their presentation tonight entitled Celestial Spheres and Torrid Zones, Medieval and Renaissance Views of the Cosmos.
Thank you very much, Kerry, for that very kind introduction. And I'm sure you're all dying to hear what we have to say after that great build-up. Don't want to disappoint you, but we're not actually going to give the lecture this evening. In fact, the people who are going to give the lecture are Professor Sacrobosco and Professor Feuerbach, who we will introduce you to immediately. These are, of course, the authors of the two most important astronomy books of the early modern period, books which you will inevitably have to read if you go to university. And of course, you're going to have to study astronomy if you go to university. Let me first introduce, from Paris, by special arrangement, Professor Sacrobosco. You may be slightly surprised by her appearance. In fact, you may be surprised to find out that Sacrobosco is actually a lady rather than a gentleman. She's from California originally, as you can tell from the name, Sacrobosco, Hollywood. Right, so we call her Hollywood, but don't call her Holly. Of course, she was educated at Oxford and then recruited by the University of Paris under their spectacular Equalitas Opportunitorum program. You are the author of a book which stands in rather dramatic contrast to one of the other people we'll be talking about tonight. That's this wretched man, Nicholas Copernicus. So I mean, we're going to tell you what we think is right in astronomy, and we're going to tell you what's wrong with Copernicus and that awful man Galileo. In fact, Copernicus's book, didn't somebody just call that the book nobody read?
That's right.
So what should we call your book?
Well, a prominent scholar has described my book as the book everybody read.
Well, maybe you tell me a little bit about it while our next guest arrives.
So I wrote, arguably the most popular scientific book ever. I, in 1230, composed a textbook called The Sphere, which was designed to teach introductory astronomy to university students. So all of my students at the University of Paris got their introduction to astronomy by reading my textbook, The Sphere. This textbook was so good that it was used in universities all over Europe. It was adopted all over Europe. Furthermore, it continued to be used from the 13th century through the 17th century. So I am, far and away one of the best-selling authors in the history of science. My text went through at least 200 editions in manuscript and over 200 in print. Many of the people whose names are now more familiar to you, like Copernicus and Kepler and Galileo and even Newton, they all read my book when they were at university. They all got their introduction to astronomy from my book. And I'm going to tell you a little tonight about my book, but first I'm going to introduce my considerably younger colleague, Professor Georg von Peuerbach of the University of Vienna. Now, although my textbook continued to be used as the introduction to astronomy from around 1230 to, as I said, around 1700, once students had taken an introduction to my introductory course, they would go on to take an intermediate course in astronomy. And the textbook for that course was called the Theorica, and this is a kind of intermediate astronomy textbook, not advanced, but intermediate. Well, around 1450 or thereabouts, this bright young thing decided that Theorica that intermediate text was considerably out of date. And so he composed a new Theorica, a sort of a new introductory text, and that too became a widely used astronomy text teaching intermediate astronomy all across Europe. In print, our texts were very frequently bound together. So university students would often buy the introductory and the intermediate text together. And so tonight, Professor Peuerbach and I are going to talk about the contents of our book, the basic kind of introductory and intermediate astronomy curriculum in universities throughout Europe. I'm going to start and talk about my text and the kind of very basic view of the cosmos, and then Professor Peuerbach will take over and give a somewhat more complex, introduce you to some of the complexities. Before I start, though, the other thing that we would like to do here is we would like to correct two very pervasive stereotypes about us medieval scientists. And the first stereotype that I'd like to address and refute is the idea that in the Middle Ages, religious authorities, meaning the Catholic Church, discouraged any study of the natural world, and that it was impossible to advance any theory about the natural world unless it corresponded to a rigidly literal interpretation of the Bible. And I want to say, first thing, that's completely false. So here is an image of the cosmos from a version of my text, The Sphere, that shows a basic picture of the cosmos, which I'll talk about in just a minute. But you see the same image in religious texts, in Bible illustrations, and other kinds of religious texts. This is the Nuremberg Chronicle of 1493. This is a depiction of the creation of the world, and you see the same image of the cosmos, this time with God and the angels outside of it. So this is a view of the cosmos that was widely used by religious authors and artists, but it's not a view of the cosmos derived from the Bible. In fact, it is not compatible with a literal reading of the Bible, and I will just state that. If anyone wants further information, I can say more in the question and answer session. But this is not really compatible with a literal reading of the Bible, and that simply didn't bother people in the Middle Ages. This view of the cosmos comes up in religious imagery, like in Bible illustrations and in the Nuremberg Chronicle, because it was believed to be the most scientifically up-to-date and accurate view of the cosmos. It was the view of the cosmos that fit empirical evidence, observational evidence, and because it was believed to be the most scientifically accurate view of the cosmos, it was the most true representation of what God had created. And so it's widely used, but Again, it's not a view of the cosmos derived from the Bible. And the second stereotype that I'd like to address, I'm going to get rid of this hat before it drives me crazy. The second stereotype that I want to address is the view that there's no progress in medieval science, that we're all just slavish followers of ancient writers like Aristotle, that we're entirely based on texts and not interested in observation. Well, that too is not an accurate representation of medieval science. If you look at this title page to a printed edition of my sphere from 1488, you see three figures. On the far side, you see Ptolemy, and in the middle, you see an allegorical representation of astronomia, astronomy, and then on the far left, Urania, the muse of astronomy. So notice two things. One, Urania is looking up at the sky, and astronomy is holding in her hands an astrolabe, and an instrument used for observation. So we were deeply invested in observation of the heavens in the Middle Ages, and in other aspects of the natural world. The other thing that I would say is that it may strike you that my text being used from 1230 to 1700 indicates a certain lack of progress in science. And that too would be inaccurate, because one of the beautiful things about my book is that it's relatively short and clearly structured. And most people who used my book, or many people who used my book in the centuries after my death, wrote plenty of commentary on it. So although it may seem that the same text was being used, actually my text gets kind of changed over the centuries, so that subsequent authors of this text or authors of commentaries on my text will sometimes disagree with me, will add in information that was not known to me when I wrote the text. So for example, most texts of Sacrobosco, of mine, after about 1500 are going to include references to voyages of exploration. In fact, one of the very earliest textual references to America comes in a commentary on one of my texts, a commentary on my text by a Spanish author. This is a bit later. This is an Italian translation of my book, and if you look on the bottom, you notice there's a globe there, and this is a little bit hard to see, but in the close-up, you can see on the very bottom, so it was very common to insert new information. So in fact, my text, and its longevity, rather than representing the kind of stagnation of medieval science, quite the reverse. It represents the kind of active vitality of medieval science, because my text was a vehicle for disseminating new ideas about the cosmos. Okay, so with those two general points in mind, let me get into the understanding of the cosmos that my text taught people. So my text deals really as much with the earth as it does with the heavens, and the two were understood as kind of interconnected, okay? So this is a series of drawings of the cosmos from actually three separate versions of my text. A couple things should be apparent from these images. One, the earth is round and it's in the center of the cosmos. So in all of these, the earth is in the center and everything rotates around the earth. One thing that's not obvious from these pictures is that the earth is very small. It's as a point in relationship to the entire cosmos. So In my text, I explain remember, I'm talking to introductory, very young university students, some of them taking their first university courses. So I give them the arguments for why we know the Earth is round. Let me share a few of them with you. So one argument that I present students with is that we know that the Earth is round because as we move around the Earth, we see different stars. So depending on where you are on Earth, you will see different stars. Now that would not be the case if the Earth was flat and the heavens were just spread out above this flat Earth. But in this case, so what this picture illustrates is a traveler moving around the Earth, and the lines represent the kind of the changing horizon line of the traveler. So when the traveler is here, you can just see everything kind of above this line. This traveler here can see these two stars. You can see everything above that line. So that illustrates that that's one of many arguments that I present, that the Earth must be round. It's one piece of evidence because as you move around the Earth, you see different stars. And again, that would not happen if the Earth was flat or indeed other shapes. Another argument for the roundness of the Earth that I present in my text is this one. If you are on the shore and you look out to sea and you see a ship approaching, the very first part of the ship that you will see will be the top of the mast, while the bottom of the lower part of the ship will remain invisible to you. And that's because the surface of the waters is curved, as this somewhat exaggerated picture shows. But those are, some of the arguments. Here's another version of that. These are some of the arguments that I make in my text to demonstrate to students that the Earth is round. Another series of arguments, I explain to students why it must be that the Earth is central, why the Earth must be at the center of the cosmos. There's a number of illustrations on this manuscript. I'm going to do a close-up here of ones on the left side. Okay, these images show arguments for actually both the centrality of the Earth as well as its small size in relationship to the cosmos. Because what you see on the top is there's the big circle, and then the green circle in the middle represents the Earth, and then the line there represents the horizon line of a viewer standing like on the very top of the Earth. And if the Earth were off-center by that much, then the stars that you would be able to see would only be covered by that arc that's cut off by the line. And the same thing kind of lower down. And that's not what we observe. On any given night, anywhere, anyone on Earth can see half of the heavens. Anyone can see half. You don't see a third of the heavens or a quarter of the heavens. You always see a half. And if the Earth were not in the center, that would not be the case. That's also an argument, actually, related to this, why the Earth must be very small in relationship to the cosmos. Because, again, if the Earth were as large, if that were proportional, then it would mean that people on different parts of the Earth would also see less than half the Earth. But that's, again, not the case. We know, because we care in the Middle Ages about observational evidence, we know that you can always see half of the heavens. So that could only be the case if the Earth is in the exact center of the cosmos and if the Earth is tiny as a point in relationship to the entire cosmos. Okay, so I do explain to students why it must be that the Earth is round, why it must be that the Earth is at the center, but I also give the dimensions of the Earth. Now, here is a point on which many subsequent commentators disagree with me, because this is a subject on which there's considerable debate throughout the Middle Ages on into the early modern period. So this text gives the diameter and the circumference. So those figures there's one set of figures for the circumference and the diameter of the Earth. But those are actually going to vary considerably depending on what version of my text you look at, because that's a quite lively subject of controversy. Okay, so let me turn from the Earth to the heavens. So I've shown this picture before, but let me explain a little more clearly what this is. This is a picture of a cross-section, if you will, of the entire cosmos. So at the center is the Earth, and actually this picture shows concentric rings of earth, water, air, and fire represented here. You want to point them out? Okay, so there's the Earth at the center, and then water, air, and fire. So the four elements, because the terrestrial realm is the realm of the four elements, earth, air, fire, and water. And then the celestial realm, which is outside, you see on here, each of the each of the 5 visible planets, the sun and the moon, are embedded in spheres, and those spheres move around the Earth. So you have the moon, Mercury, Venus, at the center the sun, Mars, Jupiter, Saturn, and then on the very outermost edge of the cosmos are the stars. So here's another kind of view of the cosmos. That one may be slightly clearer because it spells out the names of the planets, which are in Latin but are still very, very close. So one thing that I would say about the cosmos is like an onion, in that there is no space. There is no space in the Middle Ages. There's no outer space. So the entire cosmos is completely full, like an onion. So actually, let me go back. Yeah. So so each of these spheres that the planets are embedded in touch other spheres. There is no space in between them. Professor Peuerbach will have more to say about the motions of these spheres. In my text, I simply introduce students to the idea that each of the planets are embedded in one of these spheres, also called an orb, and that the entire orb or sphere rotates around the Earth. So planets do not move. They do not move through space. They do not move in paths around the Earth. They are embedded in orbs. Those orbs rotate around the Earth. Okay, so I'm going to speak a little bit about the motion of the sun and just briefly touch on the moon, and then I'm going to turn things over to Professor Peuerbach, who will go into more detail on the motions of these heavenly spheres. Okay, so when I taught at the University of Paris, and I presented these ideas about the cosmos to the class, I would typically hold one of these devices in my hand to demonstrate to the students. This is called an armillary sphere. This is why many, many texts that have my image in them also show me holding an armillary sphere. That is an actual armillary sphere from somewhat later period. So you can see these are real physical objects that were used to teach astronomy. All right, so let me explain this image. So this armillary sphere was used to demonstrate the kind of simplest motions of the cosmos, as the motions of the sun, the moon, and the stars. So let me take kind of first the sun. The sun, if we think about the sun has two motions, right? Every day the sun rises and sets. So the sun swirls. Now we're thinking geocentrically. Stay with me. The sun swirls around the Earth, rotates around the Earth on its nice orb once every 24 hours on an axis that runs through the north and south pole of the Earth. Okay, so there's the North Pole, South Pole. So if we kind of move this around, the sun, also the moon, and the fixed stars and all the planets move around the Earth once every 24 hours. So that's how we get day and night. But we also know that the sun changes position over the course of the year, right? That's how we have seasons, or that's how we observe that, why we observe that the sun will rise and set at different places on the horizon over the course of the year. Also, we have the changes in weather with the seasons, but also the changing lengths of day and night. And that's because the sun has two motions. Not only does it move around the cosmos, the entire cosmos moves around the Earth once every 24 hours, but all the celestial objects except for the stars have another motion. And that motion is represented by this thick red band, okay, which is tilted at an angle. That's actually about 23 degrees, tilted at an angle from the celestial equator, which runs kind of that line, that yellow line that's right in the middle. So the sun moves along that band. In fact, in the direct middle of that line, the sun moves around the Earth in the opposite direction, okay, once a year. Okay, so the sun's motion is two motions, one very rapid once every 24 hours, and then one very slow, a yearly motion in the opposite direction on a different axis. Okay, now that band is known as the zodiac, and there are 12 houses or 12 signs in the zodiac, and the sun moves through those over the course of a year. The sun always stays. You can see that band is made up of two lines like a belt, and there's one line that runs directly through the middle. That line is known as the ecliptic, and the sun is always on that ecliptic. Okay, so those are the two motions of the sun. And in my text, I devote the most attention to the sun. That's the celestial object that I devote most time to, with the exception of the stars. That's actually about the simplest has the simplest motions. So I might point out some other points about this. When the sun is at its northernmost point and its southernmost point, those are the solstices, the longest and shortest day of the year. That yellow line that's right in the middle is called the celestial equator. When the sun crosses those lines, which it does twice a year, those are the equinoxes, when day and night are equal. So those are some other features of the motion of the sun. Let me descend once more to the Earth and actually explain the torrid zones, which we put in the title of our talk. One of the things that I explain in my text, which actually becomes very controversial and much disputed later, is the idea that certain regions of the Earth, because of their relationship to the sun, are either too hot or too cold to live in. And so the torrid zones are the zones that are too hot to live in, and the frigid zones are too cold to live in. So these zones here are actually defined. If you took this armillary sphere and you projected it back onto the Earth, you would have, so these it would not support human life. So I told my students that it was not possible for human beings to live in the torrid zone. Now you might notice there's only, this is an earlier version of my text. So here we have kind of Asia, Europe, and Africa, and they're all kind of stuffed into the one habitable zone. There is another habitable zone on the other side, that upper zone. That is, in theory, habitable. And why isn't there anything there? It's because it's entirely covered with water. So one of the things that I say in my text is that about 7/8 of the Earth is covered by water. So really, the kind of the range where human beings can live is quite small because it's in the habitable zone. It can't be in the frigid zone, can't be in the torrid zone, but the vast majority of the globe is covered by water. And this is my absolute favorite image from a version of my text with these extremely happy fish who rule the world, literally. Now, that's an area that comes, that subsequent commentators on my text generally point out that I'm wrong about. And most versions of my text from about 1500 on, some even earlier, will point out that, that's nonsense, and that furthermore, Portuguese voyages of exploration down the coast of Africa, Portuguese and Spanish explorations, in their attempt to find a sea route to China, that all of these have shown that there are no, that the torrid zone is perfectly habitable, that there are people there, that it's, that it's actually, quite a decent place to live. So almost every reader of my text in the early modern period called me out on that one. But on the other hand, I will say in my defense that that I did, one of the things that although these regions aren't habitable or they aren't uninhabitable, there are temperature variations, of course. I also noted, you might notice the very top of that is divided into 7 climactic zones. And I also noted that, very far north, you would have, 6 months of light and 6 months of day. So I wasn't completely wrong, but I was somewhat wrong. The last thing that I talk about in my text, fairly briefly though, is the motions of the moon. Now the moon is the closest body to the Earth. It's also carried on a sphere that rotates around the Earth. It has a daily rotation east to west, so there is that 24-hour rotation. And then it moves like the sun west to east around the ecliptic, not quite, it moves through the zodiac. So whereas the sun takes a year to move west to east around the Earth, around the zodiac, the moon takes 1 month. And so I explain to students how the phases of the moon are connected to the position of the sun in relationship to the moon and the Earth. So there you have the sun and the different phases of the moon. Now if you imagine the Earth should be at the center of that, and the gold parts represent the lit parts of the moon, what you would see. So I explain how the phases of the moon work. And then I end with a discussion of eclipses. So the figure on the left is a lunar eclipse, and the figure on the left is a solar eclipse. So I explained these phenomena in not much detail. And so that's where I'm going to leave off, because the remaining celestial bodies, the 5 visible planets, have more complicated motions. And even when we get into a somewhat more technical level, the sun and the moon have more complexities to their motion than I have laid out. And so this brings us to the intermediate astronomy course, which Professor Peuerbach teaches, and which he will give you at least a taste of right now.
Thank you, Professor Sacabosco. who has laid an excellent foundation for the remarks I need to make, to introduce you to the largest objects created by God, the largest objects in the cosmos. This should be the high point of your university experience, not only understanding the structure of the world, a good part of which has been explained with great clarity by Professor Sacrobosco, but also understanding how the heavens themselves are put together in detail. Yes, now they told me I should start with a joke. And I wasn't quite sure how good your Latin was, so I wasn't sure whether I should do the one about, cur galena viam transit. Why did the chicken cross the road? Ut pars ultra atinet. It seemed to me that there was a much more appropriate one for today, which was, why did the chicken cross the torrid zone? To which the answer is, to avoid being fried. I also wanted to dispense with this wretched hat. As Professor Sacrobosco was kind enough to explain, I wrote a new Theorica. I'm come from the University of Vienna, and so we're very progressive. We actually have a new style hat, which I'm going to wear, much more comfortable and practical. So the last subject in Professor Sacrobosco's book is an elementary exposition of the mathematics of planetary motion, which also explains eclipses. Here are some pictures of eclipses from my own book, and you can see here several features which require explanation beyond simply the alignment of the bodies that creates the eclipse. So here, for example, we have a variety of lunar eclipses, which can vary from total lunar eclipses that last quite some time, while the moon, the red object, travels through the shadow of the Earth, shown here in black, to eclipses where only part of the moon is obscured, or eclipses where, because of the position in which the moon passes across the shadow, it's obscured for much less time. In the case of the sun, of course, it's the moon itself getting in front of the sun. You all know that. However, sometimes what you see when that happens is literally this. You see the disk of the moon completely in front of the sun, but a little ring of sun still around it. It's called an annular eclipse, a ring eclipse. Other times, the moon completely covers the sun. Now, this is an extremely important observation because it shows that the moon is sometimes at different distances from the Earth. The only way you can produce an annular eclipse is if the moon is further away than when it's producing a total eclipse. This forms the base, the idea that the planets can move further away from the Earth forms the basis for the explanation of the main things in planetary motion, contents of the Theorica, which I wrote then, and I'm not going to talk about this all by any means. And here, I want to quickly show you what the main problem I'm working on is by doing this and doing... Okay, where's hide PowerPoint? Why can't I shrink this thing? It won't let me. Okay, maybe I can just do this. Yeah.
We're not fully up on this newfangled
Yeah.
technology.
Okay, so now what? Okay.
No one understands 21st
No.
century technology.
Not like Kerry. We forgot to regather the screens, didn't we?
Yeah.
Damn it. Thanks for the rescue. Right. Okay, so let's try and get this thing to run now. And go. So, if you watch the night sky go backwards periodically and then resume their proper direction across the sky. This is called retrogression. And it's the biggest problem in astronomy since the ancients. And the man who first explained it sensibly was, now what? Let's get rid of that. Was Claudius Ptolemy, a good fellow. Who pointed out that there were two ways that you could explain this motion of the heavenly objects. In the case of the sun, which doesn't go backwards, all you need is for it to move around the circle. But because it doesn't move at constant speed when viewed from the Earth, it's clear that the Earth can't be in the center of the circle. So we call this an eccentric circle. The other planets, though, the ones that go backwards, he suggested were carried both by an eccentric circle and a smaller circle, which he calls an epicycle. So the big circle goes around this way, the small circle goes around this way. When they're both traveling in the same direction, obviously the planet's traveling across the sky along with everything else. When it gets to here, though, suddenly the planet starts moving backwards as far as you observe on the Earth is concerned. These are flat two-dimensional models. They're just circles. And in Professor Sacrobosco's book, in the fourth part, that's what you'll get, a very brief introduction with the names of these circles, for example. However, you might very reasonably ask, how can a celestial object conceivably move in this way? Well, maybe you can have the sun slightly off-center wobbling around. What could possibly make a planet move around in a little circle while it's carried around by a big circle? Well, the answer to that has been well known to our Arab neighbors, actually for hundreds of years, but never really taken seriously in Europe. I decided that what was needed was a textbook which presented those ideas from the very beginning. And consequently, in my textbook, every description of a heavenly body starts with a giant diagram. And what I really want to do today is explain what it is I'm trying to represent in those diagrams so you can understand the large-scale structure of the cosmos. This is the path of the sun. Previously, we've said that the path of the sun is an eccentric circle. Actually, this line is that eccentric circle. To generate that circle physically, what we do is to embed the sun in a solid ball, the white thing, which rotates. And to make the rotation eccentric, we trap that orb between two further orbs, which you can see are asymmetrical. They're thinner in one place and thicker in another. In fact, all of my planetary models use this. This is the model for the moon. You can see again the asymmetric orbs. And then the moon is not at the top. The series of rings at the top show you half of the moon on an epicycle. The center of the three circles would represent the path of the moon itself. It turns out you don't need a separate model for each planet. For Mercury, Venus, Jupiter, Saturn, Mars, and Venus, you can use this model, which looks a lot like the one for the moon. Notice we have an epicycle again at the top. And Mercury, which is perhaps complicated because it's the closest to the moon, gets this very complicated set of different things. Now, I find that people have a great deal of trouble understanding what it is I'm showing them when I talk about this being a system of orbs. And I had, as a matter of fact, a very elaborate mathematical demonstration, which I'm going to spare you because of time, showing you how, starting with a Ptolemaic eccentric, you could generate one of these orb models, basically by taking different circles and turning them into the surfaces of spheres as follows. So as time goes on, you end up with what we started with. The most useful diagram I found, however, is this one, because this shows you motion of the sun. The trick here is to get to epicycles. To produce an epicycle, you replace the sun with an orb, a ball of ether, and you embed the planet at one point on its outer surface. So as the ball goes round, the planet performs a circle, which is an epicycle, at the same time that it's being carried round by the rest of the mechanism that creates the eccentric circle. Now, we've already looked at several pictures like this in different versions of Professor Sacrobosco's book. This is a picture usefully described by Professor Magruder of the Universitatis Oklahomensis as a cosmic section. So it's a slice through the cosmic onion, in Professor Sacrobosco's words. Earth in the middle, Moon, Mercury, Venus, Sun, and so on going out. This, of course, is arranged simply to show you the relative position of things. It's not to scale. And, of course, as soon as you start having to actually account for the fact that different planets retrogress to different degrees, you have to introduce epicycles that are of different sizes. Not to mention the eccentrics. Here's a slightly more realistic picture of the cosmos in which you can actually see the eccentrics and the epicycle spheres. So here's the epicycle for Saturn, with Saturn stuck in the corner. This is Jupiter, but you can't see it very well because it's red on red. No, actually, that must be Mars. So that's Jupiter. So this is Saturn. Yes, yes, there's another. That's Saturn up here. Okay, got that. This band, the yellow band, is the sun. Inside it is Venus, Mercury, and finally the moon, with the Earth in the center of the whole thing. However, what you really want to know is how thick are these orbs really, and what do their motions look like? And that was the second thing I was hoping to show you. So let's see whether I can get this to work properly this time. And here we have Ptolemy's cosmos, the cosmos I've just shown you, drawn to scale. Let's start off in the middle. Here's the Earth. This is Africa, Europe, small damp island off the coast of Europe where nobody lives for most of the rest of India and Asia. And this, of course, is Ptolemy's representation of the world from his geography, which we now know to be incomplete because of the discovery of America, which Professor Sacrobosco already alluded to. As we move out, then, we see that the Earth is really very small in comparison to anything else, because here is the orb carrying the moon. And there's the moon in its epicycle. Moving out further, we come to a still larger epicycle carrying Mercury, and then an absolutely whopping epicycle carrying Venus. Next comes the orb of the sun. Yes, very small orb carrying the sun. Sun looks just the same as mine. Followed by the orb of Mars, which again has a huge epicycle. Outside it, the orb of Jupiter with another fairly hefty epicycle. And finally, Saturn. So, this is what the cosmos really looks like. Each of the planets is supported in an epicycle, which in turn is trapped in an eccentric. All these things are solid bodies, and the motions are kept in place by intervening orbs, which are thin in some places and thick in others, but which altogether are concentric with the center of the world, that is the Earth. You may notice some other odd things about this. For example, that these are all moving in unison. And if you look at it, they're actually moving in unison with this sun. I think that's very odd. That fellow Copernicus made a lot more out of it. You can look at that more if you want, but let's go back to the cosmos overall and talk about some of these newfangled views just to get them out of the way. Where's P? Here we go. So, interesting. Where am I? Yes. Nope, that's wrong. The thing's jumped on me. Sorry. Yes, here we go. So, this wretched fellow Copernicus, as you probably know, caused a great scandal by publishing a book in which he claimed that the sun, rather than the earth, was the center of all of the celestial motions. One good thing I can say for him is that at least he still wanted to create these celestial motions by having them made out of, pushed around by solid spheres. There's actually an obvious mistake in the most famous diagram in the book, the one showing the sun in the middle and everything getting around it, except the moon, so everybody thinks that the moon goes around the Earth. Here in my copy, you'll see I have corrected that by moving all of these outer labels down one. And when you move them down one, you can see they're not labeling the lines at all. They're labeling the orbs between the lines. And this is just as solid, as onion-like a cosmos as the ones that we were looking at before. There was some fun and games with the title as well, but I'll spare you that. Now, this Copernicus fellow has very few followers, but a couple of them are prominent. This is Johann Kepler, who you probably know as the, pains me to say it, the chief astronomical advisor to the second most powerful person in Europe, the Holy Roman Emperor. And he subscribes to this ridiculous nonsense of Copernicus. In fact, this is his diagram of it. And you can see here that there are double lines separating the zones to show that this is an orb, and this is an orb, and this is an orb, physically carrying a planet somehow or other. If you read his book, you find that this is no longer a nice, comfortable onion. If you draw everything to scale, there are enormous gaps between the orbs for the different planets. So this is a scale drawing by Kepler of the planetary orbs from his first book. And here's the orb of Saturn, here's the orb of Jupiter, here's the orb of Mars, and it goes on into the middle. You can see that there are these huge holes, which make no sense at all. Well, I mean, if you've read Kepler, you know how he wants to make sense of it. I mean, he has this ridiculous construction of inscribing and circumscribing the orbs on the regular platonic solids. You can see that these are still supposed to be orbs with a thickness, because here's an epicycle. This is the epicycle of Saturn, as a matter of fact. And here's Jupiter. You can see the epicycle again. And I mean, it's a ridiculous idea. I'll tell you how ridiculous. Why do you think this is presented as a series of goals like this, right? Why do you need to draw complete spheres? Well, I'll tell you. He was trying to get a job from the Duke of Württemberg, and he was proposing to have this contraption built as a drinking fountain for the Duke's dining table. In fact, he was promising astrologically appropriate booze in each orb, so it would be pale on the outside, red wine for Jupiter, in the middle, a fiery cordial representing the sun. So, you know, that's what Copernicanism's good for, drinking fountains. Now, this Galileo chap, let's talk about him a bit. Same nonsense. This is actually the cover of his book, rather fancifully embellished with poor old Aristotle with his bald head. Claudius Ptolemy, another fine fellow, and again, a wretched Copernicus, although this time shown as an old doggerel, still carrying his little device with the sun in the middle and things going around him. This book is going to get him in trouble. No, mark my words. Now, of course, you know, what Galileo claims he is basing his arguments on in favor of Copernicus is this contraption, which he pirated from someone in Holland, to be quite honest. Here he is, he's showing it off to people in Venice. Venice, I ask you, well. And he claims to have discovered a number of things which weak minds, like the Venetians, might think favor Copernicus. For example, he claims to have seen terrestrial features on the moon. The cosmos, which Professor Sacrobosco has very adequately explained, has a terrestrial realm and a celestial realm, and the border, oddly enough, is the sphere of the moon. So, I mean, if there's going to be any contamination of the heavens from the earth, that's where you're going to find it. It's not really very surprising that there should be, you know, terrestrial features on the closest heavenly body, the one that's literally rubbing against the terrestrial realm every day. Of course, his big thing in his first book, the one about the telescope gadget, is his discovery of these things, satellites of Jupiter, which he very conspicuously named after the Medici family, which is getting himself a better job. So here you see a little number of lights. The big round thing is Jupiter, and the little asterisks. These are the moons that he discovered going around Jupiter on different nights. And it's very interesting. Tells you nothing about the center of the cosmos, because they're going around Jupiter. And what you want to know is, what's Jupiter going around? They're not doing anything surprising. They're just performing epicycles around Jupiter. We already have epicycles. I've been showing you them all evening. So anyway, after he produced this stuff, which, as you can see, is considerably less than decisive, he claimed to have discovered spots on the sun. And that would be pretty surprising, because it's all right to say that the moon could be contaminated by terrestrial elements, but the sun's a very long way away. So this can't really be spots on the sun, because the sun is a celestial object. It's made of a single substance, and it can't change. Now, there's a much more obvious explanation for all this than saying that these are spots on the sun, and that, I mean, he's really provided it himself. He discovered 4 new things flying around Jupiter. So why shouldn't there be lots of other new things flying around the sun? Of course, when they pass in front of the sun, what you see is a little black spot, just the kind of thing that he's talking about. So these aren't spots on the sun at all. These are little planets, or planetesimals, passing in front of the sun. I just want to remind you that the basic idea, which we've seen beautifully instantiated in this completely full universe of eccentrics and epicycles, is that things like the sun move on eccentrics, planets move on eccentrics plus epicycles. And it's the Earth which is the middle. Now, the last bit of evidence that he claims to have found is that the planet Venus, when seen through his new gadget, shows phases like the moon. Well, almost like the moon. I mean, these are the phases. Notice the extreme change in size from the present phases to the full phases, which suggests, of course, that the planet is very close when it's in its present phase and a long way away in its full phase. And he looks at some other things as well, which I'll just mention in passing. So, I mean, there's Jupiter and Mars up there, and you don't really see anything particular on them. You just see them as a disk instead of as a point. But look, we knew that they were extended objects. We'd even figured out sizes for them before, so that's nothing new. But the thing at the top here, I think, is a bit of a joke. This is supposed to be Saturn, and it's got, I don't know, jug handles? These Copernicans, they think about nothing but drink jug handles, I ask you. The problem, according to Galileo, is that nobody can explain the phases of Venus. Well, it's complete nonsense. We can explain the phases of Venus. We can explain the phases of Venus. Where's the last slide? I have been denied my last two slides. I can do it by using this one. What happened? Is this a different version? Ah. Okay. Well, no, I don't want to stop. Okay. Get out. All I want are the last two. So, right, let's go back to this one. Right, here we've got the phases of Venus, which he says nobody can explain except him and silly Copernicus. Here's the explanation. We always knew that Venus moved on an epicycle. Previously, we thought the center of the epicycle was down here, right, closer to the Earth than the Sun. If you slide the center of Venus's epicycle up so that it's centered on the Sun, you see exactly the phases that Galileo observed. So, all this nonsense about discovering that the universe has a different center from the one that we've always believed. Rubbish. All he's discovered is the true center of Venus's epicycle, which is the Sun. So, what we need is a good, solid universe. A universe full of orbs with epicycles, and furthermore, where you can be confident of your place and the place of the Almighty. And with that, I'll leave you. Right. Any of the four of us will now be happy to take questions. Or comments. Please.
I was curious how predictive your model is,
Ah.
and if you have problems with changing the calendar.
No, as long as you adopt a consistent calendar.
Was the calendar consistent?
Well, it depends who you talk to.
Talking to you.
Yeah. Right. There was a big fuss at exactly this moment in history in Europe about making the calendar more accurate, as a matter of fact. Kepler and his teacher, Michael Maestlin, were on sort of one side of that, and a lot of Catholic people were on the other side of it. We ended up accepting the new Catholic calendar. But the thing I should really say is the University of Oklahoma is about to erect the statue of Omar Khayyam, who you probably think of as a poet, but who is actually an important astronomer as well. And the calendar that he devised for the Persians was actually more accurate than the calendar we use today. So if you, as I said, you pick a calendar and you get results depending on how accurate the calendars you pick. The real question, I think, is how accurate is this stuff predictably? And the answer is extraordinarily accurate. If you don't have a telescope, you will never know it's wrong. Ptolemy's models are a little bit tricky mathematically, but within the limits of observational error based on the human eye, if you start from contemporary observations to determine your constants, you can make predictions which will be yes, you're quite right. He's a bit of a problem. And he's a problem for everybody. In fact, Galileo, he's the worst problem for Galileo because the explanation I just gave you for why Venus doesn't show that Copernicus is right, that's the same explanation you'd get from Tycho Brahe. In fact, absolutely everything that Galileo claims as evidence for Copernicus can be explained by Tycho Brahe, who says the Earth is stationary in the center. And for those of you who haven't heard of it, this is a very ingenious system. The Earth is stationary in the center of the world, the moon goes around the Earth, the sun goes around the Earth, but everything else goes around the sun. So all the planets go around the sun. So he's really combining the best features of Copernicanism and Ptolemaism. Now, this is so much of a problem for Galileo that when he wrote that book that I said was going to get him into trouble, he talked about the two chief systems of the world, which were, of course, the Ptolemaic system and the Copernican system, as if he'd never heard of Tycho Brahe. He didn't want to talk about it. It was too embarrassing. I have to say, I think Tycho Brahe's wrong. The system he has causes the abolition of the thing I most want to keep, which is the celestial orbs. If you do this to scale, and he's the only person who did, then when you put Mars going around the sun, there's no way of arranging the things so that the two orbs don't permanently intersect. And if they're three-dimensional solid objects, that's just impossible. So he just quite cavalierly abolished the celestial orbs and said, oh, it's all just air. Which Kepler thinks as well. And Galileo, who knows what he thinks? Dilettante. I can see the arguments. And I'll say, actually, he has a lot of followers in Rome. The Jesuits, when the theological difficulties of Copernicus were pointed out, never mind the physical ones, which are bad enough, but the theological difficulties were pointed out, they all piled onto Tycho Brahe as an alternative because they thought his mathematics was better. Well, I just think it's a question of refining our mathematics a bit and keeping them broad. Yes?
For both of you, notice that your spheres are not perfect circles, they look like symmetry. It's the universe, it's like, well, someone's sitting on it. And I'm wondering if this motions in the heavens are supposed to be perfect, why are these spheres not perfect spheres? And B, if these spheres are real and thus moving in plane motion, don't we wind up with difficulties with their not being perfect in all dimensions equal? Wouldn't there be some grinding that kind of let the long ends go into the shorter ends?
You want to talk about that?
Go ahead.
Well, the pictures you're looking at are distorted by the projection system. They are supposed to be perfect spheres, although what you're raising is actually one of the standard objections that the Verists raised against people doing proper astronomy like me and Sacrobosco. And of course, the answer to your bumping is these intervening spheres, which appear as crescents. Now, the thing to understand is all these things are spheres, or, well, orbs, technically. They have spherical surfaces. The eccentric orbs, like this, have concentric spherical surfaces. This is one spherical surface, that's another. The intervening orbs also have two spherical surfaces, but they're not concentric. They're wider at one point and narrower at the other. As a matter of fact, the two spherical surfaces touch at one point. So, the entire system, two of the crescent cross-section orbs and an intervening eccentric orb, that whole thing is completely spherical on the outside, completely spherical on the inside, and centered on the center of the cosmos, just as God, Aristotle, Sacrobosco intended.
And so these spheres are real, they aren't calculations.
They absolutely have to be real, otherwise you can't explain physically how the planets move.
Yes, and they're the best calculation yes, there are people who argue that really what we want is all perfect concentric spheres, like that crazy Greek Eudoxus said. But you can't have that because the math doesn't work. And
And because things in the sky visibly change distance from the Earth.
yeah, so that doesn't account for observations, doesn't allow for predictive accuracy. But our models do.
Does anyone think that the moon might be close enough to produce a parallax effect from the observer on one side of the Earth to the other? Does anyone think it's close enough to adopt a localization effect?
Oh yes, Ptolemy measured it. If you read his book, The Almagest, you can find an instrument, actually called a parallactic ruler, intended for making that measurement. That was what caused all the problem with the orbs for Tycho Brahe. Before Tycho, the only parallax you could really measure was the moon. People claimed to have a parallax for the sun, but it really wasn't an observation you could make. Tycho built such huge instruments that he could measure parallaxes well beyond the moon. And so he was able to track a comet, notably the one in 1577, if memory serves, on a path which he claims would take it through the orbs of Venus, the Sun, and Mars. So I'm inclined to think that his instruments were defective, simplest explanation. They're made of ether, Aristotle's fifth element. No, it's one of these. You've got to be very careful what you say about these things, or the theologians get down on you. But it's clearly rigid because the fixed stars are embedded in it, and they're carried around once in 24 hours with no distortion, maintaining fixed positions. So it's useful to think of it as something like crystal or glass.
Some people describe it like diamond. It's like, yeah, extremely hard, impermeable, and transparent.
Right, and rigid, and as these things rotate around inside each other, they create celestial music.
Yes, that's it.
Yeah. Should I tell them the joke about the Carthaginians, or is it too late?
Not sure the relevance.
No, Other questions?
I have one more out there question. Around this time, I think maybe you're aware of the Protestant Reformation
Oh, yes.
and the split of the church and all of this upheaval.
Mm-hmm.
Is there any role for astronomy in that, or do they stay to the sidelines?
Ah, well. Mhm. In this book, Kepler, who is, of course, a second-generation Lutheran, he's a student of Philip Melanchthon, Martin Luther's main diplomat and the head of the University of Wittenberg. In this book, Kepler claims to be showing you God's plan for the world. An important part of his argument is that God is an architect, if you like, operates according to mathematical principles. One of the few forms of certain knowledge we share with God is the knowledge of mathematics. And being a Lutheran, he believes that God has constructed the world in a way that can be understood by us. It's important that we understand the plan so we can fit into it. And so he thinks, okay, how could a fair-minded God have constructed the planetary system so that I could figure out the distances? And that's why he comes up with this ridiculous contraption. Now, having said that, then, the name of his book is Mysterium Cosmographica, which I would translate as something like the sacred mystery of the cosmos. The mystery, or the real message of the book is not that Copernicus is right, it's that God is a Copernican, according to Kepler, not So, yes, there's a great deal of religious entanglement here. And I've heard it said that the Lutherans' religious views, particularly the students of Melanchthon, actively supported the spread of this ludicrous idea of Copernicus's.
I guess maybe a way to restate my question is if there's this upheaval against the church and challenging their teachings on astronomy, didn't seem acceptable to challenge their teachings on astronomy.
Yeah, I think this is one of the big problems, because I said that the system, the medieval, early modern one, this Earth-centered view of the cosmos, is not biblical, doesn't fit a literal interpretation of the Bible, is adopted because it's felt to be the best science of the day. So if the best science changes, why wouldn't you just change your interpretation of the Bible? And I think the answer to that is because of the Protestant Reformation, and because, at least from the Catholic side, is this tremendous challenge to questions about who has the authority to interpret the Bible. And I think that's where Galileo kind of runs afoul of this. I think and why Copernicus's work is read, and I mean, we made a joke about it, nobody reading it, but that's not true. People read it, people taught it. It was known among, that sort of small elite group of highly trained astronomers, and it wasn't really problematic, in part because there wasn't a lot of evidence that it was physically real, um, uh, but it becomes a problem in the 17th century when Galileo is sort of actively defending it, because he's working in a milieu where the Pope and others in the church hierarchy are feeling very much under threat. And so for some astronomer to say, well, I think you ought to reinterpret this passage of the Bible in a different way, that becomes problematic in a way that, there are plenty of kind of like medieval thinkers who actually have other ideas about the cosmos, for example, and these are not, who suggest that the Earth might be in motion, or that Venus and Mercury move around the sun instead of around the Earth. So there was some more like variety to, definitely much more variety to medieval thought. Although I have the dominant perspective, but I think that the kind of intellectual climate created by the Protestant Reformation is, you can't kind of understand these changes in cosmology and the reactions to them without that.
More questions? All right, one more joke. How many students in Sacrobosco does it take to change a light bulb? Well, actually, the answer is it depends where you live. If you're in the Arctic zone or the Antarctic zone, you don't have to change the light bulb for 6 months. Okay. Thanks for coming.